down for the next lecture by Yael. Before we start, let me tell you that we're going to have the picture taken on those steps at the coffee break before the discussion session this afternoon. So tell everybody that wants to be in the picture to be here. And so without further ado, we're going to start with Yael's fourth lecture. Yael, whenever you're ready, you can start.
Okay, thank you, Gustavo. So hi, everyone. So this is going to be our fourth lecture, one before last. And there's something that I want to finish from yesterday, because if you remember, what we did yesterday was to try to talk about recursion relations and how we can get three amplitudes recursively using these shifted momenta. So what we did in this story was to introduce, oh no, okay, this is very surprising. It shouldn't have happened. Let me try again. So we introduced, okay, I think what I'm gonna do then, this is weird because everything worked fine yesterday, right? And now I'm having trouble. So, okay, I don't know why it's doing this again. Sorry. Okay. Okay, so we're introducing this variable z, this complex variable z, and shifting some of the momenta with this z. And at the end of the day, the result that we derived was, we derived a result for the amplitude, an. Okay, I can't believe this is happening because I thought we solved this. Okay, this thing is for some reason heating up. Let me try to change cables very quickly. Okay, sorry about this. I think I know what happened, but hopefully this thing will cool down sufficiently fast and we can start. By the way, I have to, I can advertise here that what I've been doing to avoid this overheating is to prop the iPad on a book. And the book that has been super useful for this is this one by John Perling.
It's a very
you can tell John.
It's a very,
I saw that he was giving that he gave the colloquium this week.
Yeah, it's a very cool,
so really
cool
great
book. Yeah.
Really great book. Okay, so let's see what happens. You can say it's a very cool book. Okay, let me just go to where I was.
You're still not sharing the, okay.
Yeah.
Now.
I'm not sharing it. Okay, now let's see what happens. Okay, so what we did was we introduced, I think it's, the problem is that it's a little, okay, give me another minute. I'm gonna try to change cables on this thing.
Okay.
Okay, let's see. So let's try again. We'll see what happens. So we had an expression for the amplitude, which was of the form A of Z equals the left part of the amplitude on the left-hand side at the pole Z equals Zij times this propagator. Oh, actually, sorry, I wanted to write something else. So let me restart. Okay, so that was our final result. We had a sum over all the poles, AL of at Z equals Zij times 1 over P Ij squared times AR hit it's Zij. And pictorially, what this corresponded to was that we were looking at a factorization where we have legs I up to J over here. This is Pij, which is the sum of them. And over here, we have the remaining legs. And so this was our AL, this was our AR, and everything is hatted because these are the shifted variables. Okay, and so we said that with this expression, we can calculate any amplitude recursively using the lower point amplitudes. So I wanted to do one example. Actually, the first example by Brito, Cacciazzo, Feng, and Witten, who introduced this. So let's do this example. So what we're going to look at is an n-gluon amplitude. And what they did is to shift just 2 legs instead of, so it's a very, very simple shift involving just 2 legs. So we have an endpoint amplitude, 1 to n, and we're just going to choose 2 legs, label them K and L, and shift these in the following way. So we're going to take the spinner K to K hat, which is K plus Z L. And then we're going to take the spinner L and shift that to a spinner L hat, which is going to be equal to L minus z k. And that's all. All the other spinors stay as they are. And so you see that in terms of the momenta, the only two momenta that change are the ones for K and L. And so, for example, if you look at the K one, then we have K. This guy goes to, this one becomes K plus ZL times just K. And similarly for the other momentum, and you can convince yourself that in this case, the shift to K is the opposite of the shift for the momentum L. And so we had this condition on the shifts that all the shifts had to sum to zero. So this is satisfied in this case. Only two momenta get shifted and by opposite amounts. Okay. And so then we can use the end result that I just showed before, namely this thing. So now we have, in order to calculate I'm sorry, this is not A of Z. I really wanted to have A at 0. This is just A at Z equals 0. This is the amplitude of interest. So we have to look at all the different poles and look at the residues along these poles. And depending on the amplitude that you consider, there can be, of course, many factorization channels that contribute. But here, the only thing we'll do is, as an exercise, is to calculate this MHV amplitude, namely AN with 1 and 2 being negative helicity, and then all the other ones having the opposite helicity. And we already saw the end result for that. It has to be of this form. And this is actually a form that was guessed, I think I already said this, by Park and Taylor in the 90s, or actually no, before the 90s, some 80 something, I think. And then it was proved recursively, actually, by Behrens and Healy using other methods in 88. But with this shift method, we now have a much simpler way of showing the recursion. And plus, you can, as we said before, you can use this to derive all the endpoint amplitudes, not just the MHV, but everything else. Okay. So, so we know already we have the form of the 3-point amplitude for n gluons. We know that this satisfies this MHV form. That's the first in the series. And now we're going to just assume that it holds for all n's up to n-1. And then we're gonna prove this for an using this BCFW shift. And because, as I said, we're assuming that 1 and 2 are negative and all the other ones are positive. So we're going to take our L and K to be 1 and 2. So the two shifted momenta or two shifted spinors are going to be 1 and 2. K equals 1 and L equals 2. And so now it's very easy to see that we need to look at the different factorization channels. And we need to look at poles in Z. Now, since we're shifting 1 and 2, and these momenta shift in the by opposite amounts, it means that we cannot put them both on the same side. If we put them both on the same side, then this P here is just not going to depend on Z. It is going to drop out. So we have to put them on different sides. So here, for example, is one contribution that we can have. We can have one here, two here, and then everything else. Let's work clockwise right now. And this is N here, and everything is plus except these two minuses here and here. And of course, everything is headed. So all these momenta here have heads on them, but the only ones where it really matters are 1 and 2. So I can really erase the heads here and here. Okay, so that's the, these are the things that we need to consider. Again, remember that we're considering a color ordered amplitude. So there's a specific ordering here, right? And so the gluons 1, 2, 3, 4 have to appear in this particular order. Okay. So now there are two possible helicities for this gluon leg here. Let's take it to be incoming here. So then let me label its helicity by H. And over on this side, it's gonna be shifted to minus H. So since I already have 1 minus here and all pluses, this guy has to be minus and this guy has to be plus, and that's the only possibility that we're allowed to have. And this is why it's so simple to do the MHV as an example. Okay, so the only thing we, so that's the, sorry. So I wanted to say another thing. So on this side, we have 2 minuses, which is fine. But on this side, notice that we just have 1 minus, this one here. So all of these guys actually vanish, except for in one case, except for if this happens to be a 3-point amplitude. So unless on one side we have a 3-point amplitude, we don't get any contribution. So for example, we can take, this really doesn't matter, but we can take this guy to be the 3-point, or this guy to be the 3-point. That doesn't matter. But what we're going to have is a contribution from summing both of these options. We can have A3 here times 1 over P1 plus Pn squared An minus 1 here plus A n minus 1 times 1 over, so, okay, let me see what I wanted to do here. So in this side, I'm just taking 3, so that's just P1 to Pn. And this guy is P2 plus P, so this is An minus 1 of P2 up to, oh, sorry, I'm sorry. This thing with the heating up of the iPad, I think threw me off a little. So we'll have to start anew. So, okay, so I forgot, of course, to count this guy in the middle. So in one case, what we have is A3 here, where we have 1 minus, P minus, and N plus. Then we have 1 over P, let me just call it big P as before, 1 over P squared times A n minus 1 of p plus 2 minus and all the way up to n minus 1 plus. And then we have to take the same thing where we now exchange them and we have a n minus 1 on the left and a3 on the right. So now we can just stick in the expressions that we had for this guy and this guy. Remember that we're assuming that the MHV form holds for n going from 3 to n minus 1. So we can use those MHV forms and then just calculate this expression. So I'm not going to do this this exercise because I think it's a nice exercise to do. One thing to notice is that which I forgot here is that here, of course, I have minus p and not p. So this is something you have to take into account. And at the end of the day, when you plug in all these expressions, you can verify that indeed you get this MHV expression for the endpoint amplitude. Okay, so this was just one example, and as we said, we can, using this method, we can calculate all the n-gluon amplitudes. Of course, in those cases, you'll need to consider many more factorization channels, and things are going to be a little more complicated. Now, one thing that I said kind of briefly, and I don't want to go into this in any detail, is that we assumed that A of z goes to 0 at infinity. That's, of course, easy to do if we know the correct form of the amplitude using some other methods. But if we don't know anything a priori about the amplitude, that's not so, it's not so trivial to argue for that. Of course, in different cases, you usually need to take different shifts. Different shifts can have different behavior for the amplitude as z goes to infinity. That's there's a lot of literature on that, but we're not going to go into any of that. Okay, so any questions about this example?
Yeah, there's a question right here.
Sorry, I didn't quite get when you said there has to be a 3-point, otherwise it vanishes. I didn't get the argument.
Yeah, okay. So let's say that again. So, okay, so the first thing, so remember that this is an amplitude where only 1 and 2, only these two guys have negative helicities. Everything else is positive. Now, we already know, we're assuming that we know the form of the amplitude for 3 point, 4 points, and everything up to n-1. We're proving this by induction. And so we already know that for, let's say, k smaller than n, all the amplitudes where we just have pluses vanish, and all the amplitudes where we just have 1 minus and everything else is plus is 0. So, and the only thing that's non-zero is the MHV amplitude with 2 minuses, and the rest were, so if we have 2 minuses and the rest are pluses, these guys are the only non-zero amplitudes. Okay, so if we just have, so now I have an amplitude that I want to calculate with 2 minuses. These guys are minuses, everything else is plus. And And so I have to look at all the possible factorizations of this amplitude. And to begin with, a priori, I have, let's start this from the beginning. So let me say, again, this is 1 minus, this is 2 minus. And so now the question is, how do we partition the different legs? What factorization channel are we looking at? So we have two possibilities. Either 1 and 2 are on the same side. So I can put 1 and 2 on the same side. Let's just do this here. So here I'm putting, let me not worry about orderings now. So suppose I put 1 and 2 here. If I put 1 and 2 here, these are the two minuses. Everything else is plus. This side is going to vanish for sure because everything here is a plus. The only thing that can be a minus is this leg here, but the minus plus 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 vanishes. Now, furthermore, this is a channel that I don't even need to consider because here, because 1 and 2 are on the same side, this momentum here is not going to depend on Z because this momentum here is P1 plus P2 plus P3 and so on and so forth. And the Z only enters in the shifted momenta, but the sum of this stays the same. The Z dependence drops out. So this is not going to give me a Z pole. So the only interesting things to look at are channels where 1 and 2 are on opposite sides. Okay, now this guy P does depend on Z, and it does give me a Z pole. But the point is that, let's say that you have, so let's say that this is not a 3-point function. So here you have n minus 1, and so on and so forth, and they're all plus helicities. And these guys are also all plus helicities. So now, if I take this guy to be a minus, this is fine. The left side is fine because I have 2 minuses and some pluses. But this side is bad because coming in here, this helicity is plus. And so again, we have just 1 minus here. And so this part of the amplitude, the left part vanishes. So again, there is nothing here. So the only option that we can have is if either this guy or this guy is a 3-point. For example, if I just have 1 minus here, n plus here, and then all the other legs are on this side, then it's fine. So here I have 2, 3, n minus 1. Then this is fine because I can take, this is minus, these are all pluses. So I can take this guy to be a minus. Coming in here, I have a minus, and I have a minus minus plus, which is an okay 3-point amplitude. It does not vanish. Okay, so that's the story. Is this clear now?
Yeah. Other questions? No, no questions.
Okay, thank you.
So one more question.
Okay.
I just want to understand if you have a 2 plus and all others are minus, we can also be amplitude with not 0. If you have 1 plus in the left and 1 plus in the right, and O was minus, we can, the amplitude not is 0, right?
So which one did you want to have? Oh, you were, yeah.
Yes.
Oh, if you just swap them together, it doesn't make a difference. The point is, I was just, so the point is that
Just to make sure about it.
minus and all pluses for if I have more than 3 guys here, 3 or more pluses, then this amplitude vanishes. And if I exchange all the pluses to minuses, the same thing holds. We can really swap all the pluses to minuses. It doesn't make any difference. The difference is counting how many opposite helicities you have.
So you need a pair of plus and O. Okay, O is minus, it's okay, but you have this thing of the left and the right to be.
Are you asking about this one?
No. The third one, the last one. If you have.
This one here.
In the left, we have one. Yes, no.
This one?
No. This will be
bottom.
0, right?
Okay. Yeah, so in the bottom, I have, so 3 points are special, right? So 3 points can be only plus, minus, or
Exactly.
minus.
Yes.
And that's just a special case. Both of these guys are non-zero, right? We calculated them.
Right. Okay. Is it what I in mind?
Oh yeah. If you went and flipped everything here, yes, absolutely, you would.
Yes, thank you.
Everything would.
Just to
would
be
work.
sure about it.
And this is what's going to happen on the. Yeah, everything is going to work.
Oh, Yael, I have just a question for clarification. At the bottom, on the left, you have in the 3 point. Shouldn't be a plus in the coming in from the in the middle.
Yeah, thank you.
Okay.
Yeah, I'm a little. I really confused you guys today. This guy should be a plus because
Thank you.
I said this guy is a minus, which it has to be, because over here I'm allowing for something that's more than a 3 point. So this is definitely a minus, and then this is a plus. Yeah. Yeah, I can't pretend to, I did it just to test whether you were awake or not, but okay. Okay, good. So now that we really know how to do this, I did want to say a little bit about loop amplitudes, not in any great detail, but for reasons that I'll mention in a bit. So what we saw up until now is how to construct tree amplitudes from lower point amplitudes, or if you wish, how to bootstrap tree amplitudes. And now I want to talk about the same thing for loop amplitudes. So the question is, how do we bootstrap loop amplitudes? And the method that I want to describe is what's called generalized unitarity. And we'll really try to do this kind of briefly and sketchily, but it's important for a number of reasons. So again, the story here is that we want to calculate these loop amplitudes, or at least parts of them, without doing any calculation, but instead using the lower point or lower order amplitudes as an input. And again, just like in the case of tree amplitudes, the key is going to be the analytic structure and the singularities of these loop amplitudes. But once we go to the loop level, then in addition to simple poles, we can also have cuts. We can also have imaginary cuts. And these are the things that we're gonna use here. So again, what this goes back to is to unitarity of the S matrix or the optical theorem. And what the optical theorem tells you is that, remember we mentioned it in the beginning, we know that T dagger T, we know that the imaginary part of T is proportional to T dagger T. And at the level of amplitudes, what this corresponds to, what you can prove this thing diagrammatically by just looking at the different diagrams that contribute to a certain loop amplitude. So let's say this is 1 up to m plus 1, and n. If we calculate the discontinuity of this amplitude, it's given essentially by the cut amplitude. Where we cut these two propagators. In other words, these two, this propagator here and this propagator here, go on shell and lead to a discontinuity that which is, and we have this equation. This discontinuity is just given by the cut amplitude, and that's equal to the product of this amplitude here times this amplitude here. And this is something that happens first at the loop level. Just looking at this relation, you see that to leading order, there cannot be an imaginary part of T because that's going to be just higher order, because on this side you have T dagger T. So the first time you encounter this is when you look at one loop diagrams where you can have two propagators that can go on shell. Okay, so this is the thing that we're going to use. We're going to use the fact that we have this imaginary cut of the amplitude, and we know that this is determined by the product of this tree amplitude times this tree amplitude. So if we know all our tree amplitudes, we can construct from that the loop amplitude. Okay, so and then once we've done that, then you can ask the question, why stop at just two propagators? Here we had a discontinuity coming from cutting two propagators, from what happens when two propagators go on shell. But in principle, we can cut even more propagators in this loop amplitude and get some information from that too. So let's look at how this is going to work. And the first thing that we'll need is something which you've probably seen before, which is the Passarino-Veltman decomposition of the amplitude. So we know that any one loop amplitude, we can write it as a sum of box amplitudes and triangle amplitudes and bubble amplitudes. So we can write it as C for I for I, sum over I, plus sum over J, C3J, I3J, plus sum over K, C2K, I2K, where what are all these things? These are certain coefficients. And these coefficients depend on the kinematics. And then these are loop integrals. So for example, I4 of P1 to P4 is a box integral. Namely, it's the integral d4L over 2 pi to the 4th, 1 over L squared, L minus P1 squared, L minus P1 minus P2 squared, L minus P1 minus P2 minus P3 squared. And then similarly, I3, P1, P2, P3 is a triangle integral. It's d4L over 2 pi to the 4th, 1 over L squared times L minus P1 squared times L minus P1 minus P2 squared. And finally, we have the bubble, which is same thing, 1 over L squared times L minus P1 squared. So the box guys are something of this form, where you have any number of momenta in principle coming into these vertices. These are the boxes. Then we have the triangles. And then we have the bubbles. Okay. And these are just scalar integrals. There's nothing going on in the numerator. And the expressions for all of them are known. So the expressions for all the boxes and triangles and bubbles are known. So essentially, when we calculate a loop amplitude, the things that we really need to find are these coefficients. The coefficients of the box, triangle, and bubble integral. Okay, now, if you've never seen this before, then the way you derive this is the following. You just say, let's look at some loop integral, and suppose I have here L mu, and downstairs I have a bunch of propagators. Then we can write this thing as some A1 times P1 mu plus B1 times P2 mu, and so on and so forth, depending on the momenta that enter here. And then once we dot the two sides with, we can dot it once with P1, once with P2, and so on and so forth. We're going to find here L dot P1, for example, and then we can dot this side with, again, the P's and get a bunch of equations. So in the loop integral, if we have an L dot P1, we can write this as minus a half L minus P1 squared minus P1 squared, minus L squared, sorry. Minus L squared. And then in this case, one propagator is going to drop out, and in this case, another propagator is going to drop out, either this factor or this factor, and we'll end up with a scalar integral on the left. And on the right-hand side, we just get B1 times P1 dot P2, and so on and so forth. And so we can reduce the integrals to a bunch of scalar integrals like this. So this is the thing that we're going to use. Okay, now actually, this is not the full story, because you can also have over here some terms that are usually called rational terms that don't involve any loop integrals. And these are going to be, we're not going to be able to do with the with what we're going to describe today. Okay, so now the point is the following: we have this expression for the amplitude, and now we can look at the discontinuity of the two sides. So I can look at the discontinuity of this side here. It's going to be equal to this discontinuity on this side of this side here. And then we're going to get one contribution from the discontinuity of the box integrals, and then another one from the triangle integrals, and then another one from the bubble integrals. Okay. So the thing that we're gonna use is we're gonna say the following thing. Suppose we know where the discontinuities are coming from. They're coming from the cuts of the amplitude. So let's consider a particular cut. Let's take, for example, a cut where we have momenta 1, 2, up to m here. And then over here, we have the remaining guys, m plus 1 up to n. And this is L1. And this I'm going to label minus L2. So coming in here, I have minus L1. And coming in here, I have L2. So I cut these two propagators. And the discontinuity of the loop amplitude is coming from the product of this guy on the left and this guy on the right. So now we're going to use the Passarino-Veltman reduction. So this discontinuity, which I'm going to label by 1 to m, meaning that I took legs 1 up to m on one side and the remaining legs on the other side. This discontinuity is equal to the sum over C4I, the discontinuity in, again, 1 to m of I 4I plus sum over j C3j, same discontinuity in I3j, and similarly for the bubbles. Okay. And now, as we said before, all these integrals are known, the box, the triangle, and the bubble. So their discontinuities are also known. And so the point is that using this, we can fix those coefficients that we need. So if we can determine this guy in terms of lower point amplitude, then we also know these guys, and namely the integrals, the discontinuity in the box, the triangle, and the bubble, and then we can fix those coefficients, which is what we need. Okay. So now let's look at the left-hand side here and see how to determine that. That's really the that's the key. So we look at the discontinuity that I'm labeling by 1 to m of this loop amplitude. And what is it equal to? It's equal to, essentially I have to look at all the different factorization channels that are possible here. Namely, I already decided that I'm looking at this particular discontinuity. So it's these propagators with L1 and L2 that are cut. But then these guys can have different helicities. This can have some helicity H1. And I'm gonna take this one to have some helicity H2. And then the helicities on the other side are the opposite of that. So the only thing that I need to sum over here are the helicities H1 and H2. And the discontinuity is given by D4L over 2 pi to the fourth delta L1 squared delta L2 squared times A3 of L1 H1 1 to m minus L2 with H2 times A3 with L2 H2 m plus 1 up to n and minus L1 minus H1. Now, where did this come from? These deltas came from exactly the discontinuity and the propagator. Originally, we had a loop amplitude with these propagators. And each one of these propagators is of the form, for example, I over L1 squared plus I epsilon squared. Where does its imaginary come from? Where does its imaginary part come from? Where does it lead to a discontinuity? It leads to a discontinuity when L1 squared goes to 0. And then it's of the form 2 pi delta L1 squared. Okay, so this happened for each one of the two cut propagators. We replace this guy by 2 pi delta L2 squared. And this is the thing that gives us the discontinuity in the amplitude. And I wasn't careful about my 2 pi's because there's a 2 pi coming from here and one coming from here. So this should have been 2 pi squared. So this is the standard expression for the discontinuity of the loop amplitude. It's given by a product of two tree amplitudes like this. But now the point is that you can say, instead of writing this in this way, let's just sort of restore it to its original form and just look at the discontinuity in the integrand itself, whatever is under the integral. So I can also write this as the discontinuity of the sum over H1, H2, or let me write this another way, the other way around. So I have the sum over H1 and H2, the discontinuity in D4L over 2 pi sorry, I lost the thing that I wanted to write here. 2 pi to the fourth, I over L1 squared, I over L2 squared, A3, L1, H1, 1, 2, and so on and so forth. It's the same expression that appears here times A3, L2, H2, and so on and so forth. So all we did here is, instead of looking at the discontinuity of M, we're just writing the discontinuity of this integral, which is really the same thing, which is really the thing that's giving us the loop amplitude. Now, the reason this is a good thing to do is that here we just have, we can work with the 3 amplitudes that are on shell, and we can use everything that we know about them. We can, whatever things we used in order to simplify and obtain these guys, we can use at this point. Okay, so the point is that we now have the this discontinuity on the left-hand side. We know the discontinuity of the amplitude, and we can now find these coefficients of the triangle, box, and bubble. Okay, any questions about this before we go on?
I don't see any hands up, so no? Okay, you can go. I don't see questions at the moment. Yeah, go on.
Okay. Right, okay, so now let's see. I mean, I told you that we were gonna look at different cuts here. Of course, we have to understand which cuts are allowed and which are not. In principle, we need to put these guys on shell. So that's going to give us some non-trivial conditions. So the two things that we need here are, we want L1 squared to be equal to 0 and L2 squared to be equal to 0. Now, this condition just means that we fix L1 0 in terms of L1. So that means that we have 3 parameters to play with, L1 x, y, and z. And then we have this second equation, which we can write as L1 plus 1 plus 2 plus m. This whole thing needs to be 0. So that's going to give us a linear equation, 2L1 dot 1 plus 2 plus m plus 1 plus 2 plus m squared equals 0. So altogether, we have 2 parameters. We have a 2-parameter solution. Okay, and that's the standard story for the usual cut, where we cut 2 propagators. But now the idea, and I think I forgot to give the reference to this. So this generalized unitarity was introduced by Byrne, Dixon, and Kosower in the 90s. So now the idea is that we can consider more general cuts as well. Here we just cut 2 propagators, but we can also look at the discontinuities that arise when you cut even more propagators. So remember, each propagator has the form L squared plus I epsilon. And so when this L squared goes on shell, we're gonna get a discontinuity, which is 2 pi I delta of L squared. And so now, again, the story is going to be that we look at the Passarino-Veltman reduction. We look at, let's say, the discontinuity on the left-hand side when we take 3 propagators on shell, and equate that to the discontinuity on the right-hand side when we take 3 propagators and put them on shell, and similarly for 4 propagators. And then we can evaluate the contribution on the left-hand side using the different factorizations of this one loop amplitude. And from that, we can fix the differences here. So let's, so I already said this, but let's write it more explicitly. So for example, for the triple cut, we're going to take 3 of the propagators and put them on shell. So we'll have to sum over the possible helicities of the particles running in those propagators. And then we're going to have on the left-hand side, the product of 3 amplitudes, one with L1, H1, 1 to M minus L2, H2, A3, L2, H2, M plus 1 up to some K minus L3, H3, and then A3, L3, H3, K plus 1 up to N minus L1, H1. So this is going to be our left-hand side. And on the right-hand side, we will have triple cuts, namely 3 cut propagators of the box integrals and of the triangle integrals. And of course, that's it, right? The bubbles will not contribute here because the bubbles only have 2 propagators. And finally, there are the quadruple cuts. So here we cut all the 4 propagators. So here our left-hand side amplitude factorizes like this. There's some blob with some number of lines. Here I have another blob, and here I have another blob. And altogether we cut 4 propagators. And the discontinuity that we get is given by the product of these 4 amplitudes. This one times this one times this one times this one. And these are all 3 amplitudes, which presumably we already evaluated. Okay, in this case, let me label these momenta, the sum of these momenta, let me label that by K1. This is going to be K2. This is going to be K3. And this is going to be K4. And now we have more equations because we needed to set all these propagators on shell, this one, this one, this one, and this one. And in this case, it's easy to see that you just get discrete solutions. Because if we just do this exercise, so the first equation that we have is that L2, which is equal to L1 plus K1, needs to give us 0. And then we have L3, that's L1 plus K1 plus K2. This guy also needs to be 0. And finally, L4 which is L1 plus K2 plus K3, needs to be equal to 0 when we square that. And so that fixes everything, and you just get two discrete solutions. So remember that we had two free parameters before when we just got two propagators. Now essentially we have two more equations, so we determined everything. And that's the reason why you stop at 4. I mean, in D dimensions, there are only 4 propagators that you can cut. Okay, so the point is that because we cut 4 propagators here, the only thing that contributes on the right-hand side, so remember I'm equating this to the Passarino-Veltman expression. On the right-hand side, the only thing that contributes are the boxes and nothing else. So when you use these quadruple cuts, you can fix all the coefficients of the boxes. You can fix the C4s. Then using this, you can fix the C4 and C3. And using the, finally using the regular cut, where you just cut 2 propagators, or the double cut, you can finally fix the bubbles as well. Now, the reason why this is okay, let me just say one more thing about these coefficients, because you see that in this case you're going to get something very simple because you just have a product of 4 tree amplitudes. So we can actually write a simple expression for this case. So let's do that. So on the left-hand side, our integral just reduces to A1 tree of L plus, A2 tree of L plus, A3 tree of L plus, A4 tree of L plus, times 1 over L1 squared up to L4 squared, where this L plus is one of the discrete solutions that we found to the equations. Remember, the equations had 2 discrete solutions. And so this is just one of them. Plus we have the same thing with the, where plus goes to minus. So we can write a very simple expression for the left-hand side in this case, and that's going to fix for us the C4i, the coefficients of the box integrals. So with this, we can really fix the boxes very easily and extract eventually all the different coefficients. And one reason why these C2s are very useful is, remember, the C2s are the coefficients of the bubble integrals. So the C2s are the coefficients of the bubble integrals, and the bubble integrals are the only ones that are UV divergent. So the UV divergence resides in the bubble integrals. So if we're interested in the running of certain quantities or the running of certain couplings, this is the part that we really care about. And of course, it's the one that's hardest to determine, because we need, because the bubble integrals are the ones that have both they contribute both in the double cuts, in the triple cuts, and in the quadruple cuts. Sorry, I want to say the other way around. They only contribute to double cuts, but in order to extract these coefficients, we need to know the contributions of the boxes and triangles, which also contribute to the double cuts. So, but at the end of the day, if all we care about is the running, then the bubbles are the things that we care about the most. Okay, so I think that that's everything I wanted to say about the bootstrapping at the loop level. You know, for the sake of time, I didn't want to go into too much detail here, but let's see if there are any questions about that.
Questions? None so far. Oh, here's
Okay.
one. Here's one from Matthias.
Probably you're going to cover this. Will you explain how this extends to two-loop order, or to which extent these similar techniques can be used at two-loop order? So for instance, at two-loop, we don't have this nice classification in terms of bubbles and boxes and triangles. On the other side, the unitarity, of course, is also manifest.
No, so I mean, this is really all I wanted to say about the loops. Just because we, the main thing I wanted to, the main reason I wanted to point this out is for the purposes of looking at the running of anomalous dimensions. But, you know, really nothing beyond that.
Okay.
Already I'm way behind in terms of other things that I wanted to get into.
Another one.
Yeah. So something else that maybe I guess you won't mention is about chiral anomalies. So I know there's some discussion from Yutin Huang from 2016, for example, about trying to understand anomalies from loop structures from the amplitude perspective.
Oh, okay.
Right? But
so anomalies are okay. So anomalies kind of that's a very good question. Anomalies fall into sort of the story that it's another aspect of, you can think of this as, you know, relearning things that you know about QFT from amplitudes. So of course you can ask yourself about anomalies. And this is something that was done by, as you said, by Huang and collaborators. I forget exactly when, maybe 2015 or something. And what they did there was to look at what's going to go wrong if you have an anomalous theory. And essentially, the thing that goes wrong is that you don't get the correct factorization when you look at, and you don't get the correct singularities when you look at a one loop amplitude. So if you have, if your fermion content is not anomaly free, you're going to see that, and the way you're going to see that is that your amplitude is not going to factorize correctly. So this is something that was shown.
Okay. I don't see any more hands, so you can go on. See if you. There are no more questions, so you can continue.
Okay. So that really concludes everything I wanted to say about massless amplitudes. And the next subject that I want to talk about, and we'll see how much time we have to do that, is massive amplitudes and then applications. And of course, one of the reasons why once we talk about applications, depending on exactly what we want to do, but if we want to talk about collider processes, for example, where there are massive particles involved, then we really need to talk about masses. So the next thing I want to start talking about is massive amplitudes. And essentially, we're going to start by doing something very similar to what we did with the massless amplitudes. We're just going to talk about how to bootstrap these amplitudes from the bottom up. Okay. Now, let me remind you some things that I told you in the first lecture about these amplitudes. So by now, we're experts on massless amplitudes. We know how to write them. And what we need to do now, when we talk about massive amplitudes, we now have momenta that are massive. And the way we'll deal with them, as we said, is that we're going to split the momentum into some P1 plus P2, where both of these are light-like. And the thing that we need is that, of course, 2P1 dot P2 equals M squared. And we said that this choice basically boils down to a choice of the direction of, let's say, P1. Once we've done this, we can write P alpha alpha dot as PI PI. That stuff that we did in the first lecture, where I goes over 1 and 2, and that's this index here that labels these two momenta. Okay, and the relations that these satisfy are that P times PI square equals PI angle, and equals M times PI angle. And similarly, P bar times PI angle equals M PI square. And again, my notations really follow this paper. So if you want to look at my spinor notations or all the qualities I'm showing here and many, many more, then that's the one I'm following. Okay, and we also said that this index is really the little group index. For the massive case, the little group is SU2. And so this is the SU2 little group index. And under a little group transformation, PI, for example, goes to Wij, Pj, where this is the little group SU2 transformation. Okay, we also said that we can, using these, so now we have these new spinor variables, and using those, we can write the different polarizations. So for spin 1/2 fermions, Ui, for example, is given by Pi angle Pi square. And we have two solutions here, two different spinors, which is exactly what we need. And for spin 1 vectors, we can write epsilon alpha alpha dot with two indices, ij, that are symmetrized, and that's equal to square root of 2 p, oops, let me write it as p divided by m with an underline. And what this underline notation means is that these guys, of course, so I'm using an underline here. These guys, of course, carry indices I and J. So one of them has an I and the other one has a J. And because and the underline means that we're symmetrizing over those indices. So using this underline notation, it just means that I'm hiding those indices. These indices are implicit and they're symmetrized over. Now, this little group covariant massive spinor formalism was introduced by Arkani Hamed, Huang and Huang. And their notation actually uses not underlined, but bold. But it's going to be pretty hard for me to, what I should really write is something like PP. But this is going to take forever to do. So instead, I'm just going to use underline. But it's often referred to as the bolded spinors or the bolded formalism. And I'll keep talking about bolding and unbolding, although I'm just underlining things. Okay. And just to distinguish between massive and massless variables, I'll also use this bolded or underlined notation for momenta, not just for spinors. So whenever I have a massive momentum, I'm going to distinguish it by bolding or underlining. Okay, so what this means is that if we have some amplitude with some where leg I is a fermion line, so SI here is 1/2, it's going to come with an I underlined or an I underlined. So remember, this carries an index I. Okay, but there's going to be one factor of this. And if we have an external leg I that is a vector line, so spin 1, then it has to carry, it's going to come with 2 of these factors of I. So either 2 spinors of this type or 2 angle spinors of this type or 1 angle, 1 square, but it's going to carry 2 of these guys. So in other words, this carries a single I and this carries IJ symmetrized. Okay, and this is true more generally if we have some external particle with spin SI, which is equal to S, then the amplitude is going to feature 2S little group indices. And we're going to have M I1 to I to S here, which is just coming from, for example, P I1 alpha 1 to P I to S alpha to S times a reduced amplitude alpha 1 to alpha to S. So this thing has to involve 2S inner indices, and therefore it's coming with 2S of these external spinors, and it's carrying 2S indices of the little group. And remember, these are all symmetrized over, and that's exactly just reflects the fact that we're building tensors of the SU2 little group, and we can construct any representation using symmetry combinations of spin 1/2 of doublet representations, basically. Okay, and the reason this formalism is very nice is that it gives you a way of writing the amplitudes that's covariant under the little group. And when we have something that's manifestly covariant under some symmetry group, that gives us lots of handles on the objects that we're interested in. Okay. Another reason why it's very handy is that it gives you a very nice relation between massive amplitudes and massless amplitudes. And in other words, when you start from one of these massive amplitudes, it's very easy to take the high energy limit so I'm going to abbreviate that sometimes by HE, which is the same as sending the mass to 0, keeping the energy finite. Okay, so to see how, to make that explicit, let's say that I split my momentum P into P1 plus P2. So in order to get a nice high energy limit, I can decide to take one of them such that it goes to 0 in the high energy limit. So one of them, this guy, for example, I can keep finite, and this guy I can take to go to 0 as m squared over E. So let's say our momentum is in the z direction, so it's of the form E00 P. Then I can take P1 to be E plus P over 2 times 1, 0, 0, 1, and P2 to be E minus P over 2, 1, 0, 0, minus 1. And you see that this guy stays finite in the high energy limit. It scales like E, and this guy scales like m squared over E. And in this case, in the high energy limit, we're going to, our two states are going to coincide with the helicity states. So I'll often call this guy K and this guy Q. But that's, of course, just notation. Okay, so the way the high energy limit is going to work, so let's look at one example. Suppose we have a positive helicity vector. So that means that we're choosing I equals J equals 1. And if you don't remember that, we said it in the first lecture, so you can go back and look at that. So in this case, our amplitude is going to come with a factor, for example, of this type. And that means that so here we have a 1 and another 1 because I chose a positive helicity vector. And that's going to just give us KK. But all the other choices of I and J, in this case, will give us 0. So it's only the I equals 1 in this structure. It's only the I equals 1, J equals 1 that's going to survive. And it just reduces to KK. And since in this limit, the K and the P really coincide, I can just think of this as taking the original underlined spinner and removing the underline. So it just reduces to a regular meshless spinner. So essentially, to see the high energy limit, I can think of this as just unbolding the original structure. Okay, any questions about this?
No, no questions.
Okay. Okay. And so the same thing, the thing that I want to do now is to essentially repeat some of what we did for the meshless case, and ask the question of how do we, what can we do if we bootstrap these amplitudes? And one of the questions that I can ask is, if we demand consistent amplitudes, consistent factorization, and so on and so forth, can we sort of relearn some of the things that we know about gauge theory, some of the things that we know from QFT, and in this particular case, talking about massive gauge theory. So can we learn something about Higgsing in this way? And in particular, of course, one set of particles that we're really interested in is just the particles that we have in the real world. So I can ask the question, suppose I just have the particle content of the standard model, the quarks and the leptons, both massless and massive, and the gluons and the W and Z and Higgs. What are the amplitudes that I can write down that involve these guys? What are their consistent interactions? And what can I learn about the theory from that? So that's what I want to describe to you first. I guess I'm out of time. Or do I get a little more time? I mean, it depends on you.
How much do you need? I mean, yeah.
Okay, so let me go on for just a little bit.
Okay. Go.
Okay, so in this program, the first thing that we want to do, if we follow the same thing that we did for the massless amplitudes, is start from the 3 points and construct that, and then go on to higher points. Okay, so let me talk a little bit about this first step here, the 3 points. Okay, so the 3 points are a little funny, just like in they're less funny than the massless story, but still have some subtleties associated with them. So of course, we're with our convention that everything is incoming. We have P1 plus P2 plus P3 equals 0, with Pi squared equals Mi squared. Now, for some choices, unlike in the massless case, the 3 points were completely unphysical, right? Because we cannot really have a scattering like that. We have to go to complex momenta. Here, depending on the masses, we can have some physical processes. If M1 plus M2 is smaller than M3, then we can have a particle decay. But we'll work anyway in terms of complex momenta, so that we can, we're not restricted to a particular kinematics. Now, there are, of course, no free kinematic variables in this case. The kinematics is completely fixed, so P1 plus P2 squared, for example, is equal to P3 squared, and that's just M3 squared. So there's no freedom. The 3 points are completely determined in terms of the masses, essentially. Remember that in the M equals 0 case, we had either square kinematics, where these guys were non-zero and all of these guys were 0, or vice versa. So one of the things that we'll want to do is we'll want to consider sometimes the M goes to 0 limit, or equivalently take it to take the high energy limit. And so the reason we can talk about that is that our momenta are complex, and we want to approach this, we can approach this massless kinematics either by taking ij things to be order E, and these guys to be order M squared over E, and vice versa. So in this sense, we can talk about the high energy limit of E going to infinity, even though we're talking about a 3-point. We're taking our momenta complex, and so we can do this. Okay. So the first amplitude I want to look at is the one that's central to an non-abelian gauge theory, and that's the case of 3 spin-1 particles. And again, I want to start with a case that we're imagining that we have n degenerate particles of this type. All of them have mass m. So before we talked about having n degenerate massless spin-1 particles, now we're taking them all to have the same mass. And I want to look at the 3-point function. So these 1, 2, and 3 label the momenta, and A, B, and C are this extra index that we need to label these guys. So A, B, and C go from 1 to n. Okay. You can think of this as sort of a WWW amplitude or a WWZ amplitude in the limit that these guys are degenerate when you neglect the mass difference between them. Okay, so so the first thing to observe here is that what do I need in order to construct this amplitude? Again, the thing that I'm starting from is the little group. I want to see how the amplitude transforms under the little group. And so I need 1 to appear twice, 2 to appear twice, and 3 to appear twice. So, you know, I'll need something like a 1 and a 1, or a 1 and then 1 angle, or 2 angles, and similarly for the 2 and 3. Now you can, it's very easy to see that the only things that can appear is things like ij or ij. And notice now all the spinners are always, all my I and j are always underlined because I'm working with these in this massive spinner formalism. So for example, you could think that you could have something like 1, 2, 3. So here I just inserted a 2 between the 1 and the 3. But if we use momentum conservation, we can write this as 1 plus 3 times 3 with a minus sign. And that's just going to give us, first of all, the 1 can act on this guy and give us minus m1, 1, 3. Or the 3 can act on this guy and give us m3. So we can have m3, 1, 3. Okay, so the only things that we can have appear here are just products of involving 2 spinners, like an angle product like this, or a square product like this. Okay, so I think we probably should stop here to give you guys a break, and we'll go on with this tomorrow and construct the amplitude and see what sort of structure we're going to get from that.
Thanks
but let's see if
very
there are
much. Yeah,
questions.
let's see if there are some questions. Is that a raised hand? Did you want to ask a question? No. Okay, one question here, Yael.
Okay.
Hi, I didn't understand the when you take the 3 and plus 3 to take the last term one, the mass of two, mass 3, the mass of 3,
Oh.
the last number. I just not
This one?
get how you make it about the
Oh,
notation.
you mean this thing here? This
Yes.
when I did this?
Exactly.
example?
Exactly. You can
Yeah.
open a little bit just to understand what exactly you make.
Okay. So the thing that I used here is the fact that P acting on P squared gives me the mass times P angle, and vice versa.
Dirac equation in this notation.
And if you go back to, let's see if we wrote this. Maybe we did not. Maybe we only wrote this last time.
It's in the middle.
Oh, no.
It's in the middle
So
of that slide.
remember we wrote down the Dirac spinner like this. It satisfies the Dirac equation P slash minus M UIP equals 0. And you see that that's exactly what happens. The P slash, remember the P slash is this 0 sigma mu sigma bar mu 0. And so it exchanges, that's exactly what it does. The P slash changes an angle to a square and vice versa. So that's what I used here.
Yep.
So I think in more, using the notation that you're probably familiar with, this is just like a U P1. I'm not gonna commit to the bars, but you get the picture. P1 plus P3 slash UP3,
Yeah.
something like this. So one time this guy's acting, this guy is acting to the left here, and then this guy is acting to the right.
Any more questions? It's not the case. Let us thank Yael. Thanks many times, Yael. And before we break for lunch, let me tell you that just before the